There we go. Okay. So clinical trials, 2 arms, 1 treated, 1 non-treated with standard of care. So basically, you would like, in the ideal way, to have a lower patient included in the control arm because you know what is the standard of care treatment doing. So basically, you reduce that one and artificially you augment it so that you have the same statistical power for your clinical trial. So that was our goal. So how did we do? I'm going to go through a short introduction and then why we use the variational autoencoder framework and how actually we realized that we can capture much more information that usually have in a standard vanilla VAE. And then I will show some results on neurodegenerative diseases. Okay, so my main challenge, as I said, I have small data set, which are, of course, showing poor variability, although there is a large variability that it can capture. And sometimes if you run statistical analysis, you have lack of significant results and, of course, sometimes overfitting. And in most of our cases working with medical imaging, we have a very large amount of pixels, well, voxels. We can go up to 4 million. So if you imagine I have 4 million voxels for 1 patient and I have 50 patients, no statistician that would say he or she is a statistician would work with that. I did. So the question was, do we need to augment the data or reduce the dimension? Well, actually, you can do both, and both can be done using variational autoencoder. So our goal is to say, can I use variational autoencoder in a different way that is given in the vanilla one? Because if you want to generate faithful data, you cannot use the standard one, so that we can reduce the dimensionality of the data and understand what's happening in the population and do some data augmentation. So data augmentation, usually in images, you do some kind of transformation that are quite simple. Imagine now you have tabular data, you cannot do that. That would mean nothing to rotate a tabular data. Okay, so we need to be also agnostic to the types of data we have. And in addition, if you are thinking about images, well, rotating is okay up to a certain angle, because if you rotate a 9, at some point you will end up with a 6. So you will train your classifier with something that is actually not relevant. But you don't know. And in particular, if you go to images of anatomy, then you never know what is the good deformation that you can put on an image, that you can make act on an image, so that it's still in the same category. I don't know what is the types of images that will make a separation between control patient with a normal brain aging and Alzheimer's disease brain aging. Okay, so basically there is a notion of expertise that we don't have. Of course, there was a lot of use of different techniques to augment data. In particular, GANs have been used. But usually all this literature either reduce the dimension first, not to have 4 million voxels, or have above 1,000 training sample, which we never had, okay? So at the end of the day, this high dimensional low sample size setting was not treated, and VAE appears to be the good way. So what is a variational autoencoder? Variational autoencoder takes the initial guess of what encoder it is, but add some probabilistic model in it. So you have an image, let's say, or whatever data. The autoencoder tries to encode to a certain point in a lower dimensional latent space. And so that if you decode that point, you will end up with something that is similar to the input. What is doing the variational autoencoder? Your input is still encoded, but not to a single point, but rather to a distribution on the latent space, showing how variable you can be around a single point, so that at the end of the day, if you sample from that, you will be close by decoding to the entrance. So basically, I take my input, I have a distribution, and if I sample in that distribution, decoding this point will help having something close to my input, okay? So I have a notion of variability that is included in this model. So I don't know how familiar you are with variational autoencoders, but basically you can write it very simply. You have a probability distribution which is parametric. It depends on some latent variable, this encoding point, well, distribution. You put a prior distribution, of course, because you cannot work without, on this latent space. Usually the prior is just the standard normal distribution. And then you have this parametric distribution, which is when you know the encoding, the embedding point, then you know exactly how you can reconstruct the data. So this one is parametric. So how do you do now to train this when you want to maximize likelihood? As usual, but as usual, you cannot do it. So because anything is tractable. So we use variational inference. So if you write everything down, I will give you the slides if you want, but basically if you write everything down, at some point you will need to have this conditional distribution. What is the probability distribution of an embedding given X? Okay, so I need to know that. If you know this, then you can do everything. But if you don't know it, you can use an approximation, which is here simple, quite simple. This is just a normal distribution with mean and standard deviation that are depending on X, of course. However, this distribution approximates at first sight the conditional distribution that you have here. And if you do this approximation, you end up with an unbiased estimate of the log likelihood and with an elbow, so a lower bound, that if you maximize the lower bound, you will somehow try to approximate a maximum of your target distribution. If those, well, maybe some of you are familiar with EM algorithm, expectation maximization. Well, in the EM algorithm, you really try to either compute this or sample from this, whatever, to approximate completely the log likelihood. Here, you just do an approximation and you try to optimize that approximation in a family of distribution. Okay, so this is kind of different. You still have a lower bound, but in EM, you're trying to optimize the lower bound at each step. Here, you're taking a family of lower bound, and in that family of lower bound, you're trying to get the best one, right? So we're going to optimize the elbow. If you think about the model, we have actually a hierarchical generative model. So we can regenerate data. We have a prior on the latent space, so on the embeddings. We can sample from that prior, decode, and generate new observations. However, if you don't have enough data, although very simple, you have a prior that is completely non-informative. The standard normal Gaussian distribution has no meaning in the latent space. It's just something to kind of regularize the elbow, but it does not actually look like the way data are living in this latent space. So basically what you end up decoding is of poor quality. So our assumption was, well, we're going to change that. We really want to assume that the latent space is no more an Euclidean space with a standard normal distribution as a prior. We really like the latent space to have a structure that now will be a Riemannian manifold, right? This Riemannian manifold will have a metric that is locally changing, okay? Of course, this will not be a sphere, this will not be a donut, whatever, something that you think it is. Since you don't know the data, you want to adapt, and you want actually the data to inform the metric, right? You want the metric to be data dependent and to say something about the data themselves. So we will exploit the geometrical aspect for two reasons. The first one is to have something that makes the elbow closer to the target distribution. So first, for the training. And second, for sampling, we will change the distribution that we have here to a distribution that will be depending on the metric that we will get in this latent space. So basically, since we will have a Riemannian manifold with a metric on a compact set, you can get the uniform distribution on the manifold, thanks to the metric, and then sample from that. So this is what we're going to do. So how do we improve the elbow itself? Well, to improve the elbow, if you look at it, basically we need the distribution that approximates the conditional distribution to be as close as possible to the conditional distribution. So how we do that? Well, the idea was to say, either you have a way to write some deterministic transformation of a simple distribution that enables you to get at the end this conditional distribution, or you can take the probabilistic way of thinking, which is I will sample from a Markov chain that will have as a target distribution with we expect an ergodic behavior, which will have our conditional distribution as target distribution from our Markov chain. So we will have to sample in the Riemannian manifold. And fortunately for us, Girolami and Kanderhead in 2011 published a paper on how to use a simple way to sample on a Riemannian manifold if you have a chance to have G-1, which is the inverse of the metric. So basically, this is just a generalized leapfrog that you can find in their paper. So it's really well written. So we have a way, a technical way to do it. We know how to sample a Markov chain in this Riemannian manifold. So this is Hamiltonian Monte Carlo sampler, and we know that at the end, we will converge towards the conditional distribution that we expect to have. So the good thing is that this provides us with a way to do the posterior sampling. Good. It's guided by the gradient of the true posterior that we have here. We really use the underlying geometry everywhere we will introduce G-1, okay? However, the metric is unknown, okay? So G-1 is unknown, as I said. I don't make any assumption on I don't make assumption on G-1. I do a little bit of assumption. I will take a parametric form from G-1 and try to learn it at the same time as my autoencoder. So I have my encoder, my decoder, and actually I will also try to learn the metric in its parametric form, so this particular form, so that the data will both help understanding the geometrical repartition of the data. How do they behave with each other in this latent space, providing with the metric, and encoder decoder, right? So this metric has been proposed by Louis et al. In 2019. And actually, this form is really interesting. First, because you can have an easy way to parameterize this with these lower triangular matrices that you parameterize using neural network. There is a temperature of smoothness so that one point will have an influence on a larger or lower or a smaller neighborhood in the latent space. So this is a hyperparameter that you have to fix. The centroids for us, well, will be the embeddings of our data. So we have centroids. And of course, you need to regularize, because if you don't have enough data, and with respect to the dimension, you need some regularization. There are good points as well, as you have a closed form expression for the inverse metrics. And if I go back, you see here that I will have the inverse metrics everywhere. So good point. And actually, you can compute the geodesics quite efficiently Then there is another good point. You can define a metric volume element just with the determinant of G, of det G. So it's really easy to go and sample from this probability distribution that comes from this element of volume, right? So basically the metric, if the metric is high, then you know that the probability is low because you have mountains, and if you go up, really straight up on the mountains, you know that the probability distribution will drop down. So it's really the inverse, right? And you can define the probability distribution thanks to this local metric. So how do we end up with playing with all of this? So again, I have my input. I do the encoding with a simple embedding point, which is an element of the non-centered, Gaussian distribution with mu x and sigma x as parameters, right? So it depends on x. This will be moved with distribution. So I do my MCMC steps. So several Monte Carlo steps with the Hamiltonian Monte Carlo sampler. This Hamiltonian Monte Carlo sampler depends on the metric that I'm currently learning. And at the end, this ZK will be decoded so that my output here should look like the input there. Okay? So basically, in the same pipeline, I will learn how to encode, how to decode, and my metric. Okay? Do you have any question? Not yet. I have only one. Only one ZK per image, per image, but per so when you encode, you only learn that distribution. So the encoder for one image, the encoder provides you with mu x and sigma x. Then you sample a Z0, Z0. This one will be moved towards ZK, decoded, and this is one step of the training. Okay. Yeah. It's n is n could be the number of data points or a ratio of it. If you have many data, you don't have to take all of them to define the metric everywhere. So you can take a percentage of it. Questions? No. Right. You need G and G minus 1, right? No, you only need G minus 1 because det G is minus det G minus 1. Okay, so what actually happens? Yeah.
Category or something.
Mm-hmm.
Yeah, you have Hamiltonian formalism.
Yeah.
So how do you rewrite this
Actually,
Hamiltonian equation?
If you look at Jeremy paper, it's really like it's really like half steps. So instead of doing one step, you have to do a half step in between to take the geometry into account. So you double the number of steps you're doing in this discretization of the PDEs, but that's it. So it doesn't add much calculation. Okay, good. So what have we learned? Yeah.
How do you choose the K?
How do I choose the K?
In practice?
Well, the more the larger K, of course, the better are the distribution of the ZK closer to the conditional distribution. What we know in standard non-deep learning algorithm is that at the beginning, if you're not completely precise, that's not a big deal. But at the end of your algorithm, when you're trying to converge, then you have to be really close to the target distribution. So what we do is small k at the beginning so that we go and walk around, stride the support and see, and then increasing the number of iteration in here, we increase k a little bit, but we never go very far. Yeah.
Wouldn't the Monte Carlo Markov chain move the original point to another class, since the metric will bring you inside the prior distribution of all the classes, or you have I don't know.
So since we are learning the metric at the same time as the embeddings, it happens to really do the clustering itself. Oh, like here, just to illustrate what I'm going to say. We had at the beginning circles, so like this, and we had rings like this. Okay, so two categories. The circles are only different with respect to their diameter. So there is this is a 1 degree of freedom. Okay. And for the rings, we have 2 degrees of freedoms. We have the size, of course, the diameter, but we have also the thickness of the ring. So it's a 2-dimensional one. We put all of them together and we do the training so that the metric should adapt and say, well, if I move in this landscape around a data, an embedding, I should not suddenly go and look like something else, okay? Otherwise, the metric should change. It should tell me I should not go through this way. And if I want to go from one place to the other, I should move around, okay? So this is actually what's happening. This is what we expected. The metric will take and really get the information about how the data are structured in the latent space. They're not, well, in my previous life, I was assuming that the data were living in a Riemannian manifold. This is an assumption that you can talk about, but this was my previous life. Now, what we assume is that the representation, the lower dimensional representation of the data is living in a Riemannian manifold. So data are not Riemannian, but they can be represented by a Riemannian manifold where you're going to have a landscape with forbidden places and not straight lines to go from one place to the other.
So when the metric is trained, it's almost impossible to jump from a class to the other.
Right. So this is what happened here. If you look here, we had rings and circles. We choose a 2-dimensional lower latent space, two-dimensional latent space here. So easy to represent. And these are the encodings, okay? So as I said, the circles are living on the 1-dimensional manifold. This ear that you have here, I don't know what is an ear shape, but still, this is still a line, okay? So the geometry has been able to capture the fact that actually, if you want to move from one circle to the other, this is just a straight line in the Riemannian manifold, okay? And in the other cluster, well, it's 2-dimensional because we need something that is also depending on the size, but there are also different elements where the thickness of the rings is changing. So it's really 2-dimensional data. And now we have a matrix, so we can draw geodesics. So from one big circle to a small circle. So either you go straight as if it was Euclidean, or you go along the geodesic. If you go straight, well, you will jump over mountains, get back to another cluster, up another mountain, and then down. Okay, so a lot of variation in the landscape. And if you decode along that line, you will at some point have data that you construct that do not have any meaning, those ones that are up on the mountains. Data from the other cluster, And again, something that does not have any meaning. However, if you move along the geodesic, you really understand that the only thing you have to do is reduce the size of the image. Okay? Right, this was a very simple toy example. So we did it for shoes. So this is Fashionist. Clément, Clément tried with many other databases, but this one is really funny. So for shoes, there's no cluster, right? So if you try to go from one slipper here to a heel shoe, well, if you go straight, at some point you have shoes with 2 stages. So I don't think it would be interesting. But if you go along the geodesic, then at some point you really reconstruct shoes that look like shoes and that evolve slowly towards the good one, okay? So again, we were able to capture how the shoes are evolving somehow in this latent space. Okay, so as I said, we have a metric, so we can sample from this metric. How do we do that? Well, simply taking here the uniform distribution given by that metric. Okay, it's not flat, but I can define, thanks to the metric, a uniform distribution on the latent space. Happy with this. And I can use my MCMC sampler, still Hamiltonian Monte Carlo, to sample from that. So if we compare our sampler to other types of sampler that are coming from the literature, the first one is, well, train a variational autoencoder and sample from the prior distribution. Actually, the prior distribution was the prior, so it should have some meaning. That's important. This is how the rings and circle are encoded with a standard vanilla variational autoencoder, and the blue points are sampled from a standard normal distribution. And here are the decoding images from these blue points. Okay, so I sample blue points in this 2D latent space with respect to the standard normal, and then decode. Well, unfortunately, first you only have one single cluster because you don't go further away. Standard normal distribution is quite narrow. And you have things that really don't look like anything you've trained with, okay? So basically not really representative. You can go to the literature and see some other kinds of adapting prior. This one is a multimodal adapting prior. So the prior is adapted with respect to the posterior that is computing along. It's better, of course, but still you have several things that are not looking like anything that you've been training. In our situation, you sample from the uniform distribution that you've learned thanks to the metric. And then you can sample from places that are at the border. So this blue dot, I guess you see my, yeah. So this blue dot, for example, is quite on the side of the distribution, lower probability, but still. And then if you look at here, well, you have diversity, relevance, and it's not blurry. Okay, so some of those ones were kind of blurry that you don't get here. So we remove the blur, we have variability that was in the training set, and you also have the diversity that we really want, okay? Good, just a quick step aside. If you look at the vanilla VAE itself, still, you see that the rings are kind on a line, okay? There are still one on the line that you can draw. So basically, if you don't have enough computational power, we found a way to use vanilla VAE and to exploit this distribution in the latent space, produce an approximation of what would be the metric if you were assuming that it was a Riemannian manifold, and you can sample from it. So this is another work from Clément Chadebec. If you go on his webpage, you will find it. which is a geometrical interpretation of the vanilla VAE. So if you don't have enough computation power, and if you want to go to something that still exploits the fact that the VAE, for some reason that we don't know, kind of understands that there is a structure in the data that looks like a Riemannian manifold, you can exploit this tendency that the VAE does itself. Again, we don't know why and how, but still you can use that to resample. So this is another work of Clément. I'll try to accelerate. So some comparison. We wanted to know if we were really robust to many kinds of diversity. So first, lower amount of data. Okay, so we reduce MNIST and we try to resample. We use the EMNIST and try to resample. Fashion MNIST, again. Everything was, well, you have here some examples, but you can see in the paper, you will see how many quantification of those results have been produced. So Clément has shown as well that it is robust to whatever discretization parameter you use in this neural network. In particular, all the things in the paper have been done with an MLP, although we were using images. Okay, so just to show that with a fixed architecture of a network, the results were better. So if you optimize the architecture, depending on the kind of data you are using, of course, you will increase the results as well. But with a standard architecture, you still have interesting results. Right. So we use that for data augmentation. As I said, we like data. So we want to know if in this high dimensional low sample size setting, if we can augment the data in a relevant way. So how did we do? We had our input data. Part of it was used for training our variational autoencoder and the metric. Produce artificial data. With this artificial data and the training data, we train, let's say, a classifier, but you can train whatever you want. With the second part of the input data, we did some validation, cross-validate on this part, and then on the last part of the data, or on another database, we tested our results. So I will show you the classification on the test sets that we have been using for after cross-validation. Okay, on toy data. So first across data sets. So we use the classification on MNIST, of course, on EMNIST and Fashion MNIST with the baseline. So we have around 50 samples per class. The baseline is given here. And then when you augment the number of data, either by rotating, zooming, etc., or with standard VAE or with our method, then you end up with those scores. Okay, so you have the mean and standard deviation. So what you can see is that the baseline was not bad, but increasing the number of data really produces better results. And it's not just an epsilon, okay? If you look at the results, it's really interesting. What is really interesting as well is that actually the vanilla VAE does like the standard data augmentation. So if you look at here, the results are quite similar. Okay, so standard data augmentation on images is quite similar with data augmentation using vanilla VAE. So that was on this Ali. Okay, now classification result on reduced data sets. So now we use the same framework, but instead of training our classifier in the cross-validation loop with the artificial data and the real data, we remove the real data. The real data we're only used to train our variational autoencoder, and we only use the artificial data, so the blue dots, to train our classifier, okay? So this is the baseline. so with the real data. And here, just produce 200 or 2000 images, 200 up to 2000 images, and use these fake images to train the classifier. What you can see is actually that with the real data, you have a good percentage. Of course, the vanilla VAE without the information about the real data lacks capturing the variability of the data that we do capture. So at the end of the day, in the produced data, in the artificial data, we have at least the information that we had at the beginning, and actually we had a little more. Okay, so we were able to capture all the information that was in the training set and a little more information, right? So we also, well, Clément did a lot of experiment to see how robust it was across classifier, across the number of training data. So if you have a lot of data, the question was, do we at some point get something that will decrease the power, the statistical power of the classifier because we will somehow do some overfitting? No, when you don't have enough data, well, you really increase the classifier performances. But if you have enough data, if the information is here, you don't produce weird information at the end. Okay, so you really get what is in the data and no more. Right, this is what happens here. Right, so just to end up with this, what happens with real data? So the real data that we've been using are of two kinds. There are two data sets of Alzheimer's disease patients and control patients that were scanned both in the US and in Australia. We use, so here is the repartition of the population for both data sets. So basically we had 3D T1 MRI of the brains that was corrected and registered thanks to the Clinica software in the Brain Institute, so that we had a full-size brain that we also downsample to see if we can, if the effect of downsampling was a hard issue or not. So this was the process. What we did is to use ADNI, so the American data set, for training, validation, and we kept apart 200 people from ADNI for the test. We did that also with a reduced training set of 50-50 instead of 200-200. And we used the ABLE data set, so the Australian data set, just for testing. Okay, so we never use any Australian person in the training, so my algorithm has never seen any Australian Alzheimer or control, never. Right. We tried many architecture. There is a baseline that is known to be the most efficient in the literature. So here is it. Well, I'm not a very expert in this, and there is another optimized architecture that we have been constructed to that specific types of data that we are dealing with. This baseline architecture is the one that is now state of the art for ADNI, but global ADNI, so for all the images that you can find in ADNI. But this one was for the reduced data set of the ones, the subgroup that we've used. Okay, so 4 types of experience. The Bell's baseline architecture was 50-50, so 50 control, 50 Alzheimer's. Baseline architecture with 200-200. Optimized architecture in these two kind of things. Right. The first question you can ask me is, okay, when you are sampling rings and circle, it looks like rings and circle, but what if you sample in this 15-dimensional latent space, 15, so I have 4 million, and I project it on a latent space of dimension 15, well, Stephanie, if you sample from that 15-dimensional space, do we really have something that looks like brains? In here, you have 2 true patients and 2 fake. So I don't know if people are actually very familiar with brain MRIs, but when we put that in front of our medical doctors, they were always finding that this one is fake because this one is true because, and they were wrong. These ones are the fake ones. We did exactly the same thing for tabular data with anesthesiast. So we produced artificial patients with pre-questionnaires that are given to patients that will go through a surgery. So basically you have let's say 100 questions, and they fill the questionnaire so that at the end of the day, you have 100 questions. You project them onto a lower dimensional space, 10, and then you produce fake patients that would go to a surgery. So we had a test that was producing 50 fake, 50 true, mixing them together, and we had 3 anesthetists who were trying to say who was who. So I was happy that they were actually failing half of the time. And actually they were not, they would disagree on the ones that they thought would be fake. So even if they say this one is fake, their colleague would say, no, this one is true. So actually no medical doctor could make a difference between the true and the fakes. So that was a good point. Second good point, well, we want to train classifiers to better separate the population. So what are the results on the classification with respect to this population? So we have 50 control, 50 Alzheimer's disease patient, and we have the real image in low or high resolution, and then we produce artificial data. Producing artificial data, if you look at this, you have a real jump in terms of classification power, okay? And what is interesting is that you have it on ANLI, so the American that were, well, similar American were used for training, but you have the same increase for the Australian, meaning that we are able to generalize. That is not capturing only features from a very restricted population. So still American and Australian, they are Caucasian, right? We never go to some other types of data because we don't have them, but still it's a little bit of progress. You can increase the data set and still you increase the performances. And what is interesting is that, well, having high resolution images is good, but having low resolution images, but increasing the number of images is much better. So trying to have a 7 Tesla MRI in all hospitals just for that purpose of classification doesn't make sense. 3 Tesla is fine, okay? Just increase the number of data with artificial ones. Again, with the baseline and optimized CNN, we have the same kind of performances. So, yes. So if you want to use that, Clément has produced a very interesting platform, which is called Parog. So the software is open access, where you will see how to use it, how to train it. And he did it for experts, but he did it also for people who don't know how to use Python. So if you are those ones like me, well, you can still use it. And actually, he did not leave his PhD without going further. He actually tried to see how can we adapt that to the longitudinal data sets. And actually, this is a paper that is currently under review, but he manages to do the exact same thing with longitudinal data, trying to use the fact that we have a structure in the latent space that will evolve along the time. The probability distribution is given at time 0, but evolves along time so that you can sample from the probability distribution at any time, and you can also draw some trajectories. So he did many tests on different types of data that you see here. So just the same thing, trying to use the fact that the latent space of this variational autoencoder is not flat. It has a structure that is captured by the variational autoencoder, and they can use this to produce sequences as well as producing just cross-sectional data. And Agathe, who's not here, I thought maybe she's online. Agathe has done the job for what happens if you have multimodal data. So not a single modality, just not T1, but I have T1, T2, DWI, whatever, and tabular data as well. And I want to use them all for training so that at the end of the day, I'm able, if I have only one or two, to draw elements from the conditional distribution of the missing modality given the one that I had. Okay, so I want to have a really precise knowledge about the conditional distribution of one or two modality that are lacking given modalities that I have. So here are some results. Paper is also being submitted. So we really hope that all this dynamic around variational autoencoder will be interesting. And I have to say that both Clément and Agathe also produced a library to compare to other kinds of things. And now that I know that I have web up, I can show you here. Oops, come here. Up. So to be able to compare all these multimodal models, and hers is here. So this is Agathe's production, the way to improve the joint variational autoencoder. So to be able to compare to what happens to appear in the literature, you have this library. And the other one, let's see, up, and the other one is Pitae. So maybe some of you know about it. This is how to work with autoencoders and variational autoencoders. So you see how many models he has been able to implement, and the comparisons and samplers as well. So trying or not to use the geometric manifold sampler is what I showed you, but there are many others, and comparisons that you can see at the end of this web page with respect to the reconstruction and with respect to the sampling and the variability in terms of generation. So they've done a very, very good job, both. So to conclude, well, I hope you believe me when I say that this variational autoencoder is really, really interesting because it produces not only a way to reduce the dimension, but something that captures actually the way the data are arranged with each other. How do they interact? How do they evolve in a latent space? So that you can really take the advantage of that configuration to resample and not just the standard normal distribution. So it's a way to generate data which are relevant, which are variable enough, okay? And there is also something that is really interesting is if you think about it, I had data that were capturing enough, well, all the information that I had in my initial data set, meaning that I can actually take those data, leave the initial data set and only work on those data. What does it mean for medical data set? If I'm able to say that the produced data are actually not re-identifying the initial person, okay, so I have these artificial data, but with these artificial data, I'm not able to find the person that were in the training set initially, then these data are called anonymous and they can leave the place where they have been produced. They can leave hospitals without any contract. They are perfectly anonymous. They don't correspond to any patient. So these data can be used for any kind of things, okay? So we have a way to get data that are completely relevant with respect to a database. So it's a copy of the database, but anonymous. And this is really interesting for that too. Thank you.
So thank you, Stephanie, for this talk. So we have time for questions. Yes.
Hello.
Well, as far as I remember, for the variational autoencoder in the laws, you have like the KL term, so you can give some structure to the latent space. So I was wondering, when the metric is set free, it could be maybe beneficial to add some constraints to the metric. I don't know if you thought of that.
So in the elbow, you have this Kullback-Leibler divergence between the prior and the approximation, right?
Right.
What does it mean? It means that somehow the approximation should be close to the standard normal distribution, because the prior is always the standard normal distribution. Unfortunately, it does not, well, it's only trying to make the posterior distribution not escape away from zero. This is the only thing that this KL does.
Yeah.
If you remove this term, well, if you decrease the weight in front of it, the only thing is that you can go further away. But the prior at the end only attracts everything centered towards zero. If you look at any kind of latent space that I showed, yeah, you are always centered around zero, okay? Any kind of things is centered around, and this is the prior distribution which helps doing this, but that's it.
Yeah, well, the question was more about the metric itself.
Ah, the metric.
Because the metric is kind of free. I mean, it's completely dictated by the data. And I was just wondering if you add some constraint to the metric, maybe it could be
Just that.
Could be beneficial or
Inefficient? What would it be inefficient?
beneficial. Like, I don't know, if you consider a sphere.
Oh, you want to add more information on the metric?
Yeah, just, I don't know if it could help somehow.
Well, I don't know if it would help. There is a lot of literature about this. A group in Copenhagen has done things like this. However, well, in a 15-dimensional space, living on a sphere, why not just, well, you produce, well, you force the data to have a structure that actually they might not want to have. If you say that these data should live on a sphere, well, they would never live on a sphere. Well, it's a circle here, because I need a 2-dimensional subspace for the rings. So at some point, I like space. I would need more space to put the data so that they will. So we actually have one thing that we don't do is to try to optimize the dimension of the latent space. That's true. However, since the geometry is captured, if you here say, well, I don't know, I will put 5. Well, at the end of the day, this 5-dimensional Euclidean space will not be used, and you will end up with something that's projected on a 2-dimensional space and like this. So the metric somehow captures the real dimension that you need. If you constrain, there's no reason why you would do that, because you don't know what is the real dimension of the data.
Hey, thanks for your talk. So I do understand that you have a nice model that gives you accurate samples of your data distribution. What I didn't quite understand is how you can use it for data augmentation, because for augmentation, you don't only need the data sample, but also the belonging class. How do you obtain the class of your data samples?
So this is different. If you have to do the classification, if you have two classes, then you train on one class and you train a variational autoencoder on another class. I have my control patient. I have 50 images of my control patient. I train my autoencoder, produce these fake controls. Then on the other side, I take the Alzheimer's patient, train a really independent variational autoencoder, augment this to have fake Alzheimer's disease patient. What you can do, and I don't know if I had the up. What you can do is put them together and try to see if in the latent space, you have some clustering of the data. This is different. So either you do the classification, each class independently, or you don't know who's who. So you put them together and you try to do some clustering in the latent space. What is interesting is since you have a metric, you can do k-mean in the latent space with the metric. Okay, so this is Riemannian k-medoid. And you can see that actually it's not that bad. You have some issues in here, but if you look, this part here, it's actually small rings and small circles that are so small that you can barely see the dot, the black dot in the middle. So they are really looking alike. So this is why there is a mismatch in the clusters.
So we have time for one. Yeah. Question.
So I want to ask a question about this anonymity. So do you have a formalization of what anonymity is? Like, because if we like in one extreme case, if there's only one data point that you're training,
Yeah.
you should be able to get that data point from the metric back again. So like, how do we know we're anonymous?
So actually, there is no metric that is. Yeah, there is no metric that has been defined and so that you can say it's anonymous or not. There are guidelines given by the European G29 consulting group. So this is a European Commission working group on the side. So you have criteria that you can find online. However, these criteria are just words. So you have to translate this in terms of equations to quantify. So we are currently working with the CNIL in France so that they accept the way we quantify these sentences. So basically, what would it be? So it would be first, so take here, there would be a visual validation first, and then 3 quantification. The first visual thing would be, imagine I give you only these images on the right-hand side. Although you may know that guy, would you be able to say that this is the initial guy that I'm sampling around? So I have this image, this centroid in my metric. I sample around this, and this is what I do produce. Oops, sorry. And you should, well, are you able as a human being to tell me this is this guy? Okay. Knowing that this guy is in the data set, Now imagine you don't know that that guy is in the data set. Can you say this is that guy anyway? So it's visual. So if you look at the second one, I really like the second one because you have a latent space that is of 20 dimension. So all the direction are really interesting. And so around that person, you're able to produce people with glasses, blonde hair or pink hair, with dark skin and mustache. Okay, so the variability of around 1 point is really high in this latent space. We are really able to produce things that are really different from the input, from this white hair, white skin person, okay? And you have women, you have men, you have people looking on right, on the left, or whatever. So first, the visual thing is validated. Then for the quantitative, so we have to say that in the latent space, basically, one true patient, the distance between 2 true patients could be smaller than the distance between one patient and its encoder, its embedding, so that finally the distance between 2 patients would be much lower in terms of distance in the Riemannian manifold. So at the end of the day, you cannot, well, you would say that you are, the fake patient is closer to actually someone else. Okay, so these are the kind of things that we are trying to propose to the CNIL.
Our speaker again.
Thank you.
So do we have 20 minutes for our coffee break? Plus. So,
Je t'en prie. C'était un peu longue.